Welcome. Today we're going to continue our unit on statistics and probability. The first thing we're going to do is play a game. This game is based on a famous problem called the Monty Hall problem. It comes from a game show. It used to be very famous, so you might want to look that up. What you're going to do is choose a door, win a car. The way this works is you're going to choose one of the three doors. Behind one door, there's a new car. And behind the other two doors, there are goats. Let's say that you choose door A to open. Now, the host knows where the car is. He's going to open either door B or door C. And of course, he's not going to open a door that has a car behind it. So he's going to sort of narrow your choices a little bit by opening door B. There's a goat. At this point, the host is going to give you the option to either keep door A and see what's behind door A, or you could switch to door C and see what's behind door C. What do you do? Stay or switch? Is there an advantage to staying with door A, or is there an advantage to switching now that he's opened door B? What's the probability of winning the car? Now, we'll come back to this in a while, but this game sets us up for something that we call conditional probability that we're going to talk about today. And conditional probability is about how the likelihood of something changes when you already know that something else has happened. Now, hopefully at the end of this lesson, you can say, I can understand independence and conditional probability and use them to interpret data. And I can use probability to make decisions. The first thing that we're going to do is just review a little bit with a bag of beads. So this bag contains 5 red beads, 3 blue beads, and 2 green beads. If one bead is randomly selected from that bag, find the probability that bead is red. Now, if you recall our probability notation, the probability of drawing a red bead, we have 5 red beads out of 10 total beads. So the probability is 5 out of 10. And if you can reduce a fraction, you should reduce the fraction. You want that to be 1/2. Same scenario, but this time, let's find the probability the bead is green. So the probability of drawing a green bead, we have 2 green beads in the bag out of 10 total beads in the bag. And again, if we can reduce, we should. So that probability is 1/5. And then find the probability that you draw a yellow bead out of the bag. Well, you're going to see that there aren't any yellow beads. So it's impossible to draw a yellow bead out of that bag. What do you say then? Do you recall what we say if an event is impossible? The probability of drawing a yellow bead is 0. Okay, now we're going to look at 2 new cases. For case 1, in this example, I will be picking 2 beads out of the bag with replacement. Pretend that I randomly select a red bead out of the bag and then put it back. All right, so I'm going to pick this red bead and I'm going to take it out of the bag, but then I'm just going to put it right back. What is the probability the second bead I select will be red? Okay, well, if you look at the bag, it looks exactly like it did when we started, before we even picked the first bead and then put it back. That probability notation might look like the probability the second bead is red given the first was red. So, probability now that I draw a red bead, there are still 5 red beads and there are still 10 in the bag. So that probability is 5 out of 10, or 1/2. Now in case 2, I will be picking 2 beads without replacement. Pretend that I randomly select a red bead out of the bag, and this time I'm going to keep it out when I pick the second bead. I'm going to take that same red bead and I'm going to set it out on the table. Now I'm going to go draw the second bead. what is the probability the second bead I select will be red, given the first was red? Well, if you look in the bag, now there are only 4 red beads, and there are only 9 total beads. So that probability is 4/9. Think about it. Why are the answers to case 1 and case 2 problems different? In one we had 5 out of 10, and the other we had 4 out of 9. Work with your partner and then put your solutions here so that we can all see and share our solutions. In the interest of time, I'm just going to go ahead and show you the solutions. For case 1, we have what are called independent events. That means the occurrence of one event does not affect the probability of the other event. We've already seen that when we looked at rolling number cubes, flipping coins. If I roll the green number cube, that does not impact the probability of what I might get on the blue number cube. If I flip a coin and get heads, then when I flip the coin again, I still will have the same 1 out of 2 or 50% chance of getting heads on the next draw. Those are independent events. And in this case with the beads, when the items are selected with replacement, the probability for the next draw is unchanged. Those are independent events. We can say if events A and B are independent, then the probability of A given B is the same as the probability of event A occurring. You may wonder what that vertical line is between the A and the B. Well, that's just a symbol used to indicate conditional probability. We're going to read that vertical bar as given. The probability of event A occurring given that event B already occurred. And we have a formula for when we want to look at the probability that event A and B occurred. And that's just going to, for independent events, that's going to be the probability event A occurs times the probability event B occurred. Now in case 2, that was an example of dependent events. The occurrence of one event does affect the probability of another event. When items are selected without replacement, so when we took that red bead out and put it on the table, the probability for the next draw was changed. If events A and B are dependent, we can say the probability that event A and event B occur is the probability of event A occurring times the probability A occurs given B already occurred. Let's look at a few practice problems so that we can get used to this notation. So at the top, you would just read that the probability that the second bead is red given that the first bead was red. For the first example, let's look at a random sampling without replacement. Pay attention to whether you have replacement or you do not. The probability the second bead is blue given the first bead was blue. Okay, so that means that on the first draw out of my bag, I pulled a blue bead, and I'm going to set it on the table because this is without replacement, so I don't put it back in the bag. Now, what is the probability the second bead we draw out of the bag is blue? Well, looking in the bag, you can see there's 1 blue bead left and only 6 total beads left. So that probability would be 1/6. Okay, now let's look at the probability the second bead is red given the first bead was red if I'm sampling with replacement. So the first bead I'm going to draw is red, but then I'm going to put it back because it says with replacement. So that means that the second bead I draw is red. There's still going to be 3 red beads out of 7 total beads. And again, that's because I drew a bead out and then I put it back. That did not change the probability for that second draw. Those would be independent events. And then lastly, let's look at sampling without replacement. Probability the second bead is green given the first bead was blue. Okay, so the first bead is blue and it says without replacement. So I'm going to keep the blue bead out. Now look at the green. There's only 1 green bead, so that didn't change. The number of green beads did not change. It's still 1, but the total number of beads in the bag decreased because I've got one blue one sitting out on the table. So that probability is 1 out of 6. What we're going to do is we're going to take a short break, and then when we come back, we're going to talk about contingency tables and everyday situations with conditional probability.